All right, so let's do a problem. We're going to have a very small amount of steam because, of course, gases are hardly dense at all. So if you had 5 grams of steam, that would fill up quite a large volume. That's an entire evaporated teaspoon. That's quite a lot, actually. So if we've got 5 grams of steam, that would be like, water vapor, and it is at 105 degrees C. It's only 5 degrees above boiling. Here's the situation. Boiling some water. Steam's coming up. And then Mr. Estes foolishly reaches his poorly drawn hand over that steam, and he's going to get a nasty burn. So what's going to happen is that steam has to get cooled down by -5 degrees, and then the steam is going to condense. And it's going to dump out the entire latent heat of vaporization onto whatever happens to be nearby, namely me. So let's get that. If you are going to get the temperature change, you're going to need the specific heat, but of steam. So that is not on the sheet. It's not very likely that you'd be doing chemistry on a gas because they're kind of hard to capture for a high school lab. But if you look it up, you get that the specific heat of steam is 2.010 kilojoules per kilogram, which is just the same units as we've been using, joules per gram. So it's actually very similar to ice. All right, so joules per gram. So if I am getting a temperature change at -5, I just have to do Q equals M C delta T. M C delta T. And if you do 5 times 2.010 times 5, you end up with 50.25. Not a big deal at all. It only gave me 50.25 joules to cool down the steam from 105 degrees to the point where it could condense. And that's where it turns very, very badly for Mr. Estes' skin, because the heat that is lost when it condenses is going to be the latent heat of vaporization times the mass, and unfortunately that is 2,260 joules per gram times 5 grams. Yeah, this is the one that's going to do it. So 2,260 times 5 is 11,000. Oh my gosh, it hurts just thinking about it. 11,300 joules. This was basically nothing compared to that. I mean, it's not even in the same decimal place, which means if this situation were to actually take place, we're going to end up having a transfer of 11,350.25 joules. Okay, so just a word here. Because the latent heat of vaporization is so much higher than the latent heat of fusion, this is one of the reasons why steam burns are the worst. It's not just because the steam is hot, it's because of all of the energy bound up in the latent heat of vaporization. Okay, a quick word, and then I've got a demonstration to show you, and no assignment this weekend because this is coming out kind of late. So when you're actually boiling water and you see something rising out of the pan, you're not seeing steam. I'm sorry, you're not seeing water vapor. Water vapor is H2O as a gas. Water we just call H2O as a liquid. So what is steam? Water vapor is invisible. Water is visible. I can see steam. And in fact, if you think about the steam that you can get just when you open the freezer or when you breathe outside in the winter, that's clearly not very hot. So what is this stuff that is visible? Steam that is visible is actually water droplets that are suspended in the air. So the cold version is you've got humidity in the air that condenses as soon as it meets the cold, whether it's water vapor in the air in your kitchen. As soon as you open the freezer, it condenses on the cold freezer air, or water vapor in whatever you're exhaling, condensing as soon as it meets the cold winter air. But in the case of boiling water, what's happening is some water vapor does rise up, of course, because the bubbles that you see, this is for some reason a see-through pot, the bubbles that you see forming on the bottom are bubbles of gaseous H2O, that's water vapor, and then they rise up and they come up and they break the surface. So that's how you get that rolling boil. It's the surface of the water being broken up by all those rising bubbles. But the thing is, liquids and gases can mix, just like with carbonated soda. And so you end up with invisible water vapor. I'm drawing something invisible because, teacher stuff. So you've got invisible water vapor rising up into the air, but then you have little droplets of water that get carried with it. It's the droplets of water that you're seeing. Anyway, that's steam. I've got something to show you now, and then this class is done.